Hello, today we're looking at sex-linked genes. Now what this really means is basically some disorders are related to whether you are a male or female more often than not. And we can use pedigrees and things like that to determine whether a gene or a trait can be sex-linked. Let's get into it and we'll let the slides explain it. Now you have these slides in your package here, I believe. So you can go right to the package and work along. You don't really need to make, right there you go. You don't need to make any real notes on this unless I'm writing something, you can. Your only assignment for lesson 29, sex-linked genes, is to simply hand in the one sheet at the end, and then there's an extra sheet that's a little bit more challenging, and I'm going to do some of that with you, and I'm going to give you the answers for that page as well if you'd like to try it. But there is one sheet you have to do, and the other sheet is more of an optional thing where you can try it and see if you understand it. And when we get to the review on the next lesson, I'm going to do that question with you as well. So the last couple lessons, they've had like a bit of optional stuff because some of these things are a little too complicated to do in a distance ed section. So let's just get into it, and I think this will explain it. And I find students enjoy this one. So the X's and Y's of genetics. There are 23 pairs of chromosomes, and one of those pairs are the sex chromosomes. There are either X chromosomes or Y chromosomes. Now this is pretty cool. So if you are a woman, you get an X chromosome from your mom and an X chromosome from your dad. Cool. That means you're a woman, right? XX, female. So if you're a female and you're giving away your chromosomes to your kid, you can either give them half of an X or half of an X. So no matter what the woman gives, she gives an X on that last pair of chromosomes. But the man gets an X from his mother, and he can get a Y from his dad. Whoa, whoa, whoa! Look at this. This is just like a tiny little chromosome. I thought every pair of chromosomes matched up equally. Well, they do, except the sex chromosomes. The very last set of chromosomes that match up when you're being created, when your parents' DNA is combining, is the sex pair, the last pair. And if you are a male, you have an X chromosome and a Y chromosome. And look at this. There's a little bit extra space right there. And boy, that is going to become important right away. These chromosomes not only carry the genes to determine whether you're a male or female traits, but also those for some other characteristics as well. Genes that are carried by either sex chromosome X or Y are said to be sex-linked. So just like everything else, you have another pair, like say this is your sex chromosomes for one person here, a female. Well, she has 23 other pairs of chromosomes all over, right, in her cell. But say this pair up here, I made up an imaginary pair, it controlled for eye color and height, and another one controlled for hair color. Well, there's some things on this chromosome here that are controlled by that chromosome, some of your traits. Do you see where this could be a problem if you're a man? Whatever you get from your mom is what you get because there's no counterbalance. I'll explain it a little more right away. Men normally have an X and a Y combination of sex chromosomes, a big X chromosome and a little Y chromosome. Since only men inherit the Y chromosome, they are the only ones that inherit Y-linked traits. We'll get into this right away. Look at this. This is a great illustration. Look at pair 1 of chromosomes. Pair 2 from your mom and dad. Mom, 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 dad. All the way. They're all matching. They all cover the same amount of space. Except, boom, this male right here. They don't cover the same space. Now, why could this be a problem? Well, say your mother had a disease. Say your mother had a disease that she gave to you on this chromosome, and the disease was a recessive disease, and it was on this chromosome right here. Well, if your dad gave you a chromosome and he didn't have the disease, it just overwrites it and it dominates it, and you don't get the disease. But look at, if your mother gave you a disease on this part of the chromosome here, and you're a guy, so you just got a little Y, you have no other part of the chromosome to fight that trait, and it just shows up on you and you get the disease. Whereas if you were a woman and you had an X chromosome here and there was the disease from your mom, well, guess what? If there was another piece of chromosome here, it would fight that disease and you might not get it. So that's starting to make a little bit of sense. It's that extra space is really important. Now, women, as we were talking about, have two X chromosomes for that last pair. So things are a little bit different now. Look at this. Pair 1, pair 2. If there was a disease here, this one could cover it up. If there was a disease here, that one could cover it up. Same thing on the sex chromosomes this time for women. If there was a disease on this piece of the chromosome right here, well, guess what? You've got another X1 that covers that area, so you won't get the disease necessarily. So lots of the time, sex-linked diseases affect the men. The women or the female chromosomes could be the carrier. They could carry it on this, but it'll only show up in the men because they are missing that piece there. Pretty cool. Gene, I've never met a female that wasn't a double crosser because women have XX and men have XY, so they're double cross. I didn't make the slideshow. X-linked traits. Female, X and X, whereas a male has an X and Y from the mom, and then if there was a disease, it would show up, right? Men and women can get the X-linked traits since both inherit X chromosomes. Now, if this mom, say this was her daughter and her son, and she had a disease here, how could the female get the disease? Well, if the dad also had the disease, which is super, super rare. What are the odds that the mom and the dad both are carriers of a devastating disease? Pretty rare, right? So, if she had the disease here and the dad gave the disease too on his gene, well, yes, they could. The daughter could have it. And then she had a son. If she had the disease and the son doesn't have it, the son's going to get it because he doesn't have a little piece of DNA here to combat that, to take over, to dominate it. Homologous, hemizygous, no worries about that. Sex-inherited patterns for male and female children. Mother's sex chromosomes, she could give an X, she could give this X, or she could give this X, and this dad will give an X, or he'll give a Y. It's just showing the possible combinations of genes that they could give, right? The XX would make a female child, XY would make a male child. Nothing too crazy there. It's all about that extra space there. X chromosome traits. Men only have one X chromosome. Therefore, genes on that chromosome are expressed in the male phenotype, even if it's a recessive. So even if the mom has a recessive trait here, the boy will get it. Her son will get it because there's nothing to override it, to dominate over it. Now, it could be traits and not diseases, right? Obviously. We don't have to talk about diseases. That's a little bit like dark. But normally when you're looking at sex-linked traits, you're normally looking for diseases because there's a lot of known diseases that can be pretty fatal that are sex-linked, and we know that. X-linked traits. In women, a recessive allele is on one X chromosome, is often masked on their phenotype. Many have a dominant normal allele on one of their X's, but more rarely they have them expressed in their own phenotypes. Right? So as long as it's a daughter and she has the weak trait, the other one, inherited from the other person, takes over it, you don't even see it. It's not a problem. X-linked traits. In humans, at least 120 genes are known to be X-linked. So on the sex chromosomes, there's about 120 things on that X chromosome that are coded in your body. Genes for hemophilia. What does hemophilia mean? It means that your body has an inability to stop bleeding if you are cut. And that doesn't just mean externally. That means if you get hit or internal bleeding or bruising, you will bleed to death internally unless you seek medical help. I had a great friend growing up as a kid named Corey. He's still alive, don't worry. But we couldn't even play catch with Corey because if we threw the ball too hard at his hand, he would bruise, he'd get internal bleeding. He would have to go to the hospital, sometimes for days. If he would cut himself even the slightest, he had to go to the hospital. It was very scary, right? Hemophilia is a sex-linked trait. Red-green color blindness, night blindness, and muscular dystrophy are all known to be sex-linked. Hemophilia. We talked about that right now, the bleeding one, right? An X-linked genetically inherit recessive disease cannot clot their blood, severe bleeding from minor cuts, mostly in males. And this is Queen Victoria's family. And she was a known carrier of hemophilia. And they traced her family line and they could predict the chances of her children having hemophilia. Pretty interesting. It mostly showed up in the men. This poor little guy right down here. All right, let's take a look. So, for example, if the mother is a carrier, if the mother has it, so she's carrying one X that has a disease, well, if she has a dad, if she marries a man with hemophilia, guess what? Every boy's going to get it. But the boy will get it. There we go. If she married a man without hemophilia, it would still show up in some of the boys. Take a look at this chart and pause it if you need to and kind of say, if she didn't have it and he had it, all they would produce is carriers. And if she didn't have it and he didn't have it, they would never have it as well. This part is pretty interesting, right? I'll do a Punnett square for you later where you can see what this means right away, okay? If that's a little confusing, but if you want, pause it right here and take a look at that chart and go, how does that make sense? What would his DNA combo be? I'll draw a chart right away, but this is pretty fascinating. Red-green color blindness. It's an X-linked disease. You cannot perceive red and green the same. Most often it affects males. So these are some colors, right? You should be able to see the number 21, 68, and 57 there. Some people can't. And obviously, since we're videotaping this, it might be a little bit bizarre and it probably doesn't show up very well, but maybe you could see it. And I put these slides in the Google Classroom as well. Right? 58, 18, I can't see that, but I think that's the letter E, and 17. I'm on a weird angle. And muscular dystrophy, characterized by a gradual, irreversible wasting away of your muscles. An X-linked trait most and often passed on from sons to their mothers. Now, a personal story, there was a child that I taught until he passed away in an old school of mine, and he had muscular dystrophy, and we were friends with the family, and the mother really had a hard time mentally. Not that it was really her fault, but she knew that it was a sex-linked trait, so she knew it was her gene that gave this to her son, that eventually he got very, very sick and passed away, and it was very hard on her. So tracking genes is kind of sensitive. It's tough sometimes, right? But it begins to weaken the legs of boys by age 3 and gets worse every year. There is no cure, and the inflicted normally die by age 30. A good story about the child. He was an amazing graphic designer, and he could work on computers right up until some of his last years. And so he would do graphic design and animation. It was what he was passionate about. He had his own place in the graphics room in the school, and that's kind of where he spent all of his days and did the things he loved and things like that. So at least he was able to do some stuff that he really was passionate about. Let's move on, right? So there we go. If she has it, and it turns out to be a boy, and it can't combat it, he can get muscular dystrophy. Okay. Y-linked traits. Now, this is a lot less common. There's not a lot of traits that the Y chromosome carries that the X doesn't have already, because realistically, the X is so much bigger. But let's look at some Y things that if you're a boy, your dad could have given to you, right? The Y chromosome is small and therefore does not contain many genes. Y-linked diseases are very rare, only passed from father to son. Example would be infertility. Another one is an amazing one. Hypotrichosis pene. Hairy ears. Yep, you heard it right, folks. Can happen later in linked. You know, I had a hair growing out of my ear the other day, and Lisa said, oh, well, don't want to end up like that. Well, maybe I could put some gel in it and comb it back. You never know. So that's the end of the slides. So what your assignment is to go to this page, which is right after, and do this questionnaire called It Is All in the Genes. Right there. So find that in your book. I'm going to find it right here. It's all in the genes. So you could do this section here. Okay, that's cool. That's cool. And you're going to take a picture of that and submit it to me for assignment 29. Now, there's another extra section you can do here, which is the extra page. And you don't have to do this, but some of you are going to like it, and it's kind of cool. So there is the sheet, and you might want to try it. And there is a question like this on the test review, but like I said, I'm going to do it. But I want to show you the answers to this page in case you're deciding, hey, you know what, I want to try this. So if you'd like to try this on your own, you might need to look at the answers for the first question I'm about to show you, and then you might be able to do the rest of the sheet. So take a look at this. What you need to do when you're doing tracking of sex-linked traits is to actually, right here, first of all, a couple has 4 children, all of whom are boys. What are the chances that their next child will be a girl? 50-50. That's not really even related to anything we did. It's always 50-50 every single time you have a kid. But here we go. This is fascinating how you set it up, right? Duchenne muscular dystrophy is a recessive sex-linked disorder. A man and a woman who are both free of the disorder have 2 children. Their eldest son develops muscular dystrophy while their younger son is free of the disorder. Determine the genotypes of the parents. Well, the mom must have had it on 1. Right? She had it right there. And the dad has X and a Y, and the Y can't carry anything, so we leave that blank. So we put, right? Mom, normal. Mom with the disorder. Dad meets with her, normal, 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 overrides the disorder. Since the mom has normal there, it's no problem. But right here, she has the disorder and the Y chromosome has nothing. You have to leave it blank on the Y because the Y can't carry it. Therefore, this child right there, 25% chance of disease. Males. 25% normal female, 25% carrier female, 25% normal male, and 25% diseased male. Now, if you want, like I said, this is only optional. If you're interested in it, you can try the next 2 questions. And I'm going to give you the answers. So take a look at them now if you'd like. You don't need to submit this page. You only need to do the last one. But here you go. You can look at the rest of the answers right there. Okay, so please do the questions again right here. It's all in the genes. Do that, submit it in for assignment 29, and we're moving on to the review and the 3 hardest questions on the review on pedigree, sex-linked genes, and dihybrid crosses. I'm going to do for you just so you get a little bit comfortable with them, and the rest you're on your own. So we'll see you soon for the final assignment of this unit, and then we're moving on to chemistry. Take care.